So to load this it took a while. We'll be looking at the questions one by one and solving them. Already we are quite late, it's already 13 minutes. So the first question says you are given an integer array nums odd length, return true if the middle element nums exactly appears once in the array, otherwise return false. So equal to nums dot size. If x is nums of mid, then count plus plus count is greater than 1. Return false, else return true. Okay. We forgot to declare count, so let's quickly declare int count equal to 0. True, and this should be false. Okay, accepted. Move to the next one. So this question says you are given an integer array nums of length n and an integer k. A pair of indices is called valid if j minus I is greater than or equal to k. So the distance must be at least k, and nums of return the maximum value of nums of I plus nums of j among all the valid pairs. So okay, this is also kind of implementation question. So let's take initially the maximum is nums of 0. Let's take it minus 1 and actually you can take it in minute, it will be better, because here also the things are 10 power 9. Max would be equal to maximum of max and nums of I minus k. So along with this nums of I can be paired with the maximum, and we would be returning the answer. Okay, seems fine. 13, this should be 14. Okay, done. Done. You are given two binary strings s1 and s2 of same length n. You can perform the following operations on s1 any number of times in order. What are the operations? Choose an index I such that s of I is 0 and change it to 1. So you can flip a bit if it's 0. You can set a bit. You can set an unset bit. Choose an index I such that I lies between, and both s1 of I and s1 of I plus 1 are 1. You can change the both characters to 0. So you can either change 1 0 to 1, or you can change 2 1s to zeros. Return the minimum number of operations required to make s1 is equal to s2. Okay, you need to make s1 is equal to s2. So maybe I can implement this. This is also a kind of implementation question. Let's take it SNT because I hate typing numbers. N equal to s dot size if n equal to 1. Then you take 0 operations, and if s is equal to 0, actually it should be string 0, and t is 1, t is 1, in that case you take one operation. Okay, so if t is 1, it would take one operation. S is t, then it would take 0 operation. If they are not same, it would take one operation. Otherwise there is no other case. Okay, there is no other case, but still you need to return something, because so either it would be same or it would not be same, so you can just simply keep it return 1. Okay, so otherwise let's take number of operations is equal to, so this is a random base case kind of thing that came into my mind. I think it can be handled also, I don't know. So if s of I is equal to 0 and t of I is equal to 1, if this is equal to 0 and this is equal to 1, what I can do, I can simply write this. It would take one operation. Okay, or if s of I is equal to 1 and t of I is equal to 0, then also it would take one operation. But we need to have additional checks, like if I plus 1 is less than n and s of I plus 1 is equal to 1. Okay, s of I is already 1, s of I plus 1 is also 1, then you can change this. And one more thing should be checked. What is it? T of I plus 1 should be 0, then only you can change this bit. T of I plus 1 should be 0, otherwise you can't change it. And this would take one operation, but how would I handle moving to the, like, I need to skip it, right? So I can do an extra I plus plus here, and do an extra I plus plus here, and otherwise it would take two operations. And finally I would return answer. Let's see if this works or not. So this is taking one operation, 3 operations. This should return one operation. What's the problem here? So the thing is, when s1 is 1 and s2 is 0, I cannot really change it. So rather I would write this as else if s of s is equal to 0 and t is equal to 1, then only I can change this and return 1. Otherwise else I should return a -1. Else I should be returning a -1. So the third case returns -1, fine. Rest everything is alright. You are given 3 strings, word 1, word 2 and target. Your task is to count the number of ways to form target by choosing characters from word 1 and word 2. So you need to choose characters from word 1, word 2 and form the target under the following conditions. For each character of target, choose one matching character from either word 1 or word 2. The chosen indices from word 1 must be, so you need to choose a subsequence. The indices should be strictly increasing, that means it's a subsequence. And then choose indices from word 2. This also should be a subsequence, strictly increasing. At least one character must be chosen from both word 1 and word 2. Okay, so it's some sort of LCS kind of vibe. It's giving some sort of LCS kind of vibe. Okay, so it's some sort of like LCS. You check for 2 pointers. I guess in the DP state we need to maintain 3 pointers, like some I, J and K. You need to maintain some I, J and K, right? That's how it would work. I would match characters that way. Instead of matching in 2 sequences, I would match from 3 sequences, something like that. So what's the size of this? Target length is whatever. Let's take it int n empty. It can be done using DP. And modulo. So let's take it const long mod is equal to 1e9 plus 7, and we need let's say, okay, let's take these strings globally. Let's take them as string A, B and C. Okay, let's take them as string A, B and C. Now forget about the DP. Let's add the recursion first. Let's take long int I, int j on the string B, and int k on the string target, which is nothing but C. So if k is equal to target's length, t is the target length, by the way, I need to return whether did I take both characters or not, like the string from did I take characters from both strings or not. So I should be returning, did I take from string A, did I take from string B, did I take I characters from string A, and did I take I characters from J characters from string B. And if I and J are greater than 0, that means I took characters from both the strings. Okay, otherwise this is the kind of base case thing. It's actually the base case. Otherwise what I can do is, maybe I can take some int ptr is equal to, starting from I plus 1, ptr, since I need to pick subsequences, ptr less than or equal to n, ptr plus plus, if a of ptr minus 1 is equal to c of k, if it matches the current level of character on which k is pointing to. If it matches, then answer equal to answer plus recursion of ptr. With this ptr I can extend it, and j would remain the same. Since k is matched, I can move k to the next level. Okay, can move k to the next level. So next, coming to, let's take some ptr2 or ptr2, yeah, ptr2 is fine. ptr2 equal to j plus 1. I would do the same thing with j. ptr2 less than or equal to m ptr2 plus plus. What I can do is, if b of y minus some b of ptr2 minus 1 matches the current character which we are pointing to on the C thing, then answer equal to answer plus recursion of, I won't change this time, this would become ptr2, this would be, and k would be equal to k plus 1. We will be matching the next one. And once after this is over, I guess we should be having our answer. So we will be returning the answer. Okay, we'll be returning the answer, and we need to assign the global variables first. A equal to word 1, B equal to word 2, C equal to target, and n equal to a dot size, m equal to b dot size, and t is equal to target dot size or secret dot size, whatever you can write it. Till now we haven't done dp. We need to start the recursion from I is at 0, j is at 0, k is also at 0. So this would be the brute force recursion version. Let's see if this runs. If this runs, we can easily convert this to dp. It's 5 4 2. Let's see, 5 4 2, fourth test case 1 1. So the recursive approach works. Everything has a length of 100 itself, nothing exceeds length 100. So let's dp this. Better keep long dp. So 101 101 101, and before calling the recursion mem set dp minus 1 size of dp and dp of I, j, k is equal to answer. And before starting the computation, check if dp of I, j, k is pre-computed or not. If it's not pre-computed, then compute it, otherwise directly return dp of I, j, k. That's it. Once again, let's have a check if this works. 5 4 2 1 5 4 2 1. Did I dp this properly? Cache check is right here, computation is right, everything is right. Let's submit this. I hope this is clear. Yeah, done. So 4 problems are done. So that's it for today. Not bad. If I was a little bit quicker, like if the loading didn't give me trouble, it used to be really great. Could have solved it faster. So yeah, I don't think other problems require explanation, or should I explain? So yeah, after this break, like I took a short break, not actually very short, took a break. So I hope the first question is clear. We just need to check the middle element is unique or not. So once you compute the mid, you need to check if its count is 1 or not. If its count is greater than 1, then it's not a unique one, otherwise it's a unique one. Next thing, valid pair sum. You are given integer array nums of length n and an integer k. A pair of indices I, j is called valid if, okay, and j minus I is greater than or equal to k. So it's the only thing is the beauty of implementation. Nothing is very complicated here. So what am I trying to do is, if I try to put the maximum every time, which is k steps before nums of I, if I try to put the maximum which is k steps before nums of I, it could be k steps or greater than or equal to k steps. Like if let's say k is 5, let's say there's a maximum which is 5 steps, 6 steps, 7 steps, 8 steps, or any steps behind nums of I, but greater than k. It's greater than 5 or equal to 5. Such maximum I would consider and add nums of I to it to maximize it. So initially I don't know which would be the maximum, so anyways nums of 0 would be the maximum for everything. Okay, I can always ensure that if I start from some kth index, nums of 0 would always stand as a candidate maximum for everything. Okay, so nums of 0, if I take it would be at 0. Now if I start from the 0 plus kth index, which is nothing but the kth index, and go all the way till n, if I find a maximum which has a difference at least k from the I, which has a difference at least k from the I. And since the loop is increasing, if I just take the case where it's exactly k, it's absolutely fine. I can iterate through all the previous elements who make difference k, and answer equal to maximum of this maximum which I picked and nums of I. Okay, so this is the second one, a pure implementation question. Coming to the third one. Okay, coming to the third one. So given two binary strings s1 and s2 of same length, you can perform the following operations on s1 any number of times in any order. Choose an index I such that s of I is 0 and change it to 1. Otherwise choose an index that lies between 0 and n minus 1. And when both s1 of I and s1 of I plus 1 are 1, you can change both the characters to 0. So this is also another implementation question. You just need to, not an implementation, I would say it's greedy kind of. So what am I trying to do is, there's a case where n equal to 1. Why we need to take this case separately is, when n equal to 1, you cannot apply the second operation. So it stands as an exception. Since you cannot apply second operation to this, it stands as an exception. So this extra kind of edge case, we need to take it. So if n equal to 1, if there's a 0 in s, if there's a 1 in t, I can make this 0 to 1 using one operation. I can make this 0 to 1 using one operation, using the first operation. But if there's a 1 here and a 0 here, I cannot perform any operation, because to make this I would require another adjacent one here which I don't have. So I cannot really do this. So in this case I am returning a -1. And there comes a third case. The third case is where both are equal, 0 0 and 1 1. Okay, so this is a separate case, this is a separate case. In this case I need not apply any operation, I can directly return 0. So these are the three cases which I wrote, and in all other cases there would be at least 2. So there would be a presence of adjacent character, and I can always ensure that if I can solve this for two things, I can solve it for the remaining also, because 2 things is actually harder than when there are more elements. So 0 0 1 1. So this is one case, 0 1 1 1. This is another case. So I've changed this. Next is 1 1 1 1. Next is 1 0 1 0. Next is 1 0 0 1. Are all the cases covered? So for things we should take 0 1 and 0 1. So how many would be there? Or either all are zeros. Okay, all are zeros, all are ones. 0 1 0 1 1 1. 1 0 1 1 is also there. 1 0 1 1. So all these cases we can notice that actually we need not take all these cases. We can do some simple observations. One thing is, if it's a 0 and 1, if it's somewhere at I, it's a 0 and 1. S of I is 0 and T of I is 1. Then in one operation I can change this 0 to 1. So there would be one operation. Next, S of I is 1 and T of I is 0. This is one case. Where you need to change 1 to 0. To change 1 to 0, there should be an adjacent one. Right? There should be an adjacent one. We don't know what is there here still. There should be an adjacent one for sure. To change this one to 0, there should be an adjacent one. So I have two cases from here. One thing is, if there's a 0 here, in one operation I can do this. S is this, T is this. In one operation I can do this, right? I can change both of them to zeros. In one operation I can do this. But what if there's a 1 here, what would I have to do? I first have to convert both of them to 0, 0, 1, and make this thing as 1, so in this case I would require two operations. And otherwise, if I plus 1 is less than n, what would happen? I plus 1 is less than n. That means this is the last one. I need to make this as 0. And since this is the last one, if it had a previous one, it used to get paired here itself only. When we were checking, when I was here, then only this one also used to get paired and everything used to be alright. But that's not the case. That means always when there's a last one and you are reaching the last one, you are able to reach the last one, that means the previous digit which you came from was a 0. So never mind whether it was changed or it was a 0 already, never mind. And what you can do is temporarily assume this to be a 1, and when this is the 0, so when you change this to, so in one operation you are changing this to temporarily changing this to a 1, so it would take one operation, and let's say there's 0, to convert this you take another operation. So in this case also you are taking two operations. But what if there's a 1 here? So still when you are here, you have already computed something for this thing, and when you assume this is temporarily 1, when you assume that this is temporarily 1, you are assuming this. So to make this, it would cost you one operation, and that previous operation is already computed. So this is already the case. You have already computed it to be 1. Next thing, from here what you should do, that 1 is already added from this statement, this if statement. Due to the virtue of this if statement, already answer plus plus is done when I was here. Now when your I is here, you're temporarily making it as 1, and you can now make this as 0. It would take you one operation to make this as 0. And how many operations would it take to make this as 1? So it's already 1, so you can always make this as 1. So once again it would take you two operations. So whenever one of these conditions fail, I can always ensure that it's taking me two operations only. So this would work. Next thing, you can do this if you're familiar with LIS style of DP. What does LIS style say? LIS can be done using knapsack also. LIS, if you don't know, it can be done using knapsack also. Okay, you can do it using knapsack, but LIS, if you do with knapsack, you can just solve the LIS problem. You won't be able to solve other LIS style of DP problems, like maybe longest bitonic subsequence, longest mountain array, or for that matter maximum subarray sum. All these kind of things you cannot solve. So LIS pattern is basically this. So you'll be standing at an element. You'll be standing currently at some element. The idea of LIS pattern is this. So let us discuss 3 problems before jumping to this problem, so that the idea of this pattern is clear. So the 3 problems I would be discussing are, one would be a subsequence one would be a subarray one. The first one would be always LIS itself, because that's the fundamental thing. So let's say this is what you have. These are the elements in an array. Currently you don't know any numbers for these elements. So if I want to compute the LIS that is till here, so far, LIS so far, I want to compute LIS so far. So when I want to compute alias so far, I need to check whether this element can be appended to any previous prefix. This element can be appended to any previously occurring prefix. I need to find this element whether it can be appended to any previously occurring prefix. Let me show you the code for this alias so that you understand better. Longest increasing subsequence Leetcode. So for every level I am iterating over the previous indices. I guess this is in Java way. Is this then this is the tabulation one. Let me show you, somewhere there would be a memorization one. Yeah, this is it. So if I'm standing currently at some level, if I'm currently standing, let's say here, I would check, can I append this at lis ending at here? Can I append this at lis, a prefix of lis ending at here? Can I append it to this one? And this is what I'm trying to check. So what would happen? All the prefixes would be, recursion of previous would be returning the prefix at previous, recursion of level is the prefix at level. So at the end I would iterate over all the prefixes and find out what's my actual maximum, what's the actual longest increasing subsequence. Since all of them store the lengths, I would iterate over all the prefixes and find the globally maxima of all the prefixes, all the prefix lengths. So this is the idea of alias using this form of, or this pattern of DP, which is nothing but extension DP. We can call it as extension DP because you are checking whether this element can extend any previous alias. This element can exist or not, extend or not. Okay, so how are you checking that one? If array of previous is less than array of level, this level would contribute another increasing element to the existing prefix. So this can be appended. So you append this and do length plus 1. That's the basic idea. The next problem I can show you is Russian doll envelopes. So this is also based on the same idea, and don't think any solution would have the exact same code which I'm trying to show. So I need to sort the envelopes because I did this way. So let's do some other question. I did it using the lower bound thing. So if you don't know, alias can be computed using lower bound also. But anyways, this can also be done using the same approach. So what else can I show you? Longest bitonic subsequence. Okay, so this is here. You don't have any submissions for this problem? Don't think I have. I guess it should be in some different account. Okay, this idea is also same. This time you need to consider two kinds of things. I guess somewhere there it should be in my GitHub somewhere. In DP alias style, and all these problems, if you see, it's alias style only. Whenever you have to compute a subsequence, it is mostly alias style. So here also it's a bitonic subsequence. You would consider two parts. One is decreasing is true, so the bitonic would look like something like this, right? So till here you'll consider something, till here you'll consider something. I think you can do this. Okay, I think you can do this, you can understand this logic. So similarly, once again here also and you can also do it with prefix as well as suffix. It shouldn't be necessarily the ending form, like it can be starting also. The format can be starting way also. So in this case I've written starting code because that was the first thing that came into my mind. So the thing is, if k characters are matched, k characters are being matched, so here k characters would always be matched. K is the number of characters that is getting matched, or the current character which you are matching. Both are exactly the same. If t characters are matched, that means whole target string is matched. But there is a condition. At least one character must be chosen from both word 1 and word 2. At least one character from both word 1 and word 2 must be chosen. So I must be greater than 0 and j must be also greater than 0. And so this is the case. This is the base case. All the other times what would happen is you will take a long answer, which is number of ways. You need to compute number of ways so that you can pick a subsequence from either word 1 or word 2 which is equal to the target. Okay, so let's take pointer equal to I plus 1, pointer equal to I plus 1, pointer less than or equal to n, pointer plus plus. So what does it mean? You're considering every suffix that starts at I. In the previous code, longest increasing subsequence all the way, we were considering prefixes. Because why were we considering prefixes? Is there any particular reason for it? There is no reason for it. Whichever first comes into your mind, just do it. If prefix comes into your mind, do it with a prefix. If suffix comes into your mind, do it with a suffix. There shouldn't be any problem. Okay, you can do this using prefix also. I hope everyone would try to do this with a prefix variant. This time you should take n and m in that case, or something like that. Or maybe you can take I only, but you need to check previous equal to 0 to I. That's what you can do. So both things are fine. You can do it in both the ways. So if this character matches with the current character which I'm trying to match, so c of k is the current character which I'm trying to match. So if it matches, answer plus equal to recursion of, you can take this suffix, take from this suffix. Now I is at pointer, j doesn't change anyway, and now we can match for the next characters. And this is the same thing written for b subsequence. So you can either pick a subsequence from A, or you can either pick a subsequence from B, whichever gives you like you're counting things, right? So you're counting both the possibilities. You can either pick from A or pick from B. But if this condition is not true, it would return a 0. So it would not be counted. Only when this condition is true, it would be counted as a valid one. It would be counted as 1. So this is the code which I wrote. So I hope I always like to explain things this way briefly, so that there's a scope to try multiple things. If I give you a closed form answer for this one, like you need to follow a template, you should always pick prefixes or you should always pick suffixes. When this word comes, this pattern only must be used. These kind of things restrict you to solve some good problems. So let's say some problem doesn't require DP at all. Let's say there is some subsequence problem that can be done using greedy. Because I have restricted you all the way that whenever subsequence comes, I should use this kind of DP. The moment something like this happens, your mind thinks in the wrong direction. So I don't want that to happen. So that's it for today. These are all the problems of today's contest.